When I was at school, I often hated being asked to memorize something without actually knowing why something works. If I give you the example of 2 squared equals 4, simply put, that's 2 times 2. 2 to the power of 1, obviously 2, and then anything to the power of 0, in this case 2 to the power of 0, was equal to 1. I wondered why is that? Why is anything to the power of 0 equals 1? A video that I watched recently by Khan Academy gave a good intuition, was that if you took 2 to the power of 2, you can actually write it as 1 times 2 times 2, where the 1 sits in front of the number that you multiply. And that kind of makes sense. If I did 2 to the power of 1, it would be 1 times 2. If I did 2 to the power of 0, that would equal 1. Makes sense, seems to work, and that makes me like and enjoy the subject a bit more. The same way, e to the power of 0 is also equal to 1, but my teacher at the time gave us a better idea. You can express e to the x as a polynomial. 1 plus x plus a half x squared, and so on and so forth. So if you evaluated it, e to the 0 will just be 1 plus lots and lots of zeros, still just be 1. Wow, that's pretty unsurprising. But when I was doing chemistry, we used to cover kinetics. And one of the things that we covered in kinetics was a rate determining step. The rate determining step didn't really make much sense to me. It's all well and good telling me that the hydrolysis, and I should change it to a bromine than a chlorine, because bromine's a better leaving group, of this reaction, which obviously produces an alcohol, is first order with respect to this. So we normally sit there and we write something like this, and if shame I didn't get the connectivity right, but there we go, that'll work. And then you could often, as per maths, you could just write that. But what does that mean? You know, it's all well and good saying that this exists, but what does that actually mean? Well, even before A-levels, we covered the idea of an exothermic reaction and an endothermic reaction. That was energy. And I should actually make this a bit straighter, but oh well. And this was some kind of reaction coordinate. This here would be your activation energy. Likewise for an endothermic, it could obviously be a lot bigger. And you actually just took a very simple application of this graphing idea, which we call reaction profiles, to kind of understand how a slow step, or a rate determining step as it's often called, works. If I took my SN1 reaction that I've just drawn above, which gave me the alcohol, the first step is a dissociation of the carbon-bromine bond. And obviously plus Br minus, but no one really cares. And then your hydroxide would attack to form that. Of course, noting the fact that this here would be planar, so the hydroxide can attack here or here. And if I move down, I can actually draw a reaction profile for this. That's my reactant. And it will go over a barrier, which you can know as the activation energy. And for those of you that are really pragmatic, there you go, some reaction coordinates. This is the first barrier that I have to get over to form my planar intermediate. So that's what we call intermediate, and this here is what we call a transition state. And for those two terms, we're going to come back to them a lot later on. When the hydroxide attacks, we're going to go over another barrier. But notice that this barrier here is a lot smaller than the one on the left. Because this barrier is a lot bigger, this step that encompasses this arrow is a rate determining step. If I have enough energy to get over this step, then I'll have enough energy to get over this step here. That's really what it is. If I have enough energy here, I have enough energy here. So that's what you normally refer to as the fast step, and this is what you also refer to as the slow step. That's slow step, and that's the fast step. Of course, your first step doesn't always have to be the fast step. And if I'm able to do this, my fast step could also be my first step. And I'm going to give you an example in a second to explain that. I could have a situation that exists like so. This activation energy is a lot smaller than this activation energy. So this here would be my slow step. This one here would be my fast step. The fact that I have to have enough energy to get over this barrier means that this barrier will always be overcome as long as I have the energy for this. If I can't get over this barrier, I will never be able to reach the products here. I will always just roll back down towards my intermediate, or even, in some cases, roll back down to my reactants. So the equilibrium, which we'll discuss also, will always go that way. And an example of this that I've found in the literature is nitrogen monoxide and oxygen. As I said, because the first step is a fast step, it will always exist in an equilibrium. But the second step, so that's 1 and that's 2, will always be the slow step. If I haven't got enough energy to get over this barrier, then I'll never have enough energy to go over to the products, even if I have enough to get over my first barrier here. And that's really it. There isn't really too much of a difficulty in understanding this. But often it's not really well illustrated what a slow step might be, or what a rate determining step might be. So that's all that the video is about, just summarizing what a slow step is and what a rate determining step is in the context of kinetics.